Let us come to this problem sections. Here we will solve some problem on Arrhenius equation. So Arrhenius equation means the another form Arrhenius equation is, that is a logarithmic form. So all these problems will be based on logarithmic problems. So practice these problems and make your concept more strong and clear. So at 0 degree centigrade, for the decomposition reaction of N2O5, rate constant is 7.87 into 10 power minus 7 per minute. If the activation energy for the reaction is 24,700 calorie per mole, so calculate rate constant at 25 degree centigrade. So what is the logarithm form Arrhenius equation? So just write it down here. So here log of K2 by K1 for two different temperature, we will have a two different rate constant value which is equal to activation energy divided by 2.303 R, and this is the temperature of first temperature minus this is the second temperature. So highest temperature minus lowest temperature. So here we have given two temperature, 0 degree centigrade, 25 degree centigrade here. Okay, and activation energy also given here. So three values given here, and we have one more rate constant. So putting the value of all each and everything. So here K2 we need to find out. That K2 means higher temperature. So higher temperature, the rate constant of higher temperature is we need to find out. So log of K2 and K1 is given here. This is 7.87. So right here 7.87 into 10 power minus 7. And activation energy is given here 24,700 calorie per mole, so 2.303 and multiplied by 2. So here temperature is 1 by 273, lower temperature minus highest temperature 298. So on solving we will get here, so this will be your 25 minus 273. So directly I am writing this answer. On solving you will get here K2 is equal to 3.587 into 10 to the power minus 5 per minute. So this is our answer. A first order reaction is 50% complete in 30 minutes at 27 degrees centigrade and 10 minutes at 47 degrees centigrade. Calculate the rate constant for reaction at 27 degrees centigrade and 47 degrees centigrade. Second question is you have to find the activation energy for this reaction, and third is the energy of activation for the reverse reaction if the heat of reaction is minus 50 kilojoule per mole. So heat of reactions we need to find out, that is the forward activation energy minus the backward activation energy. So this is the sum total given here, that is the delta H. So we need to find out. So first is the for rate constant of the reaction. So rate constant is, this is half life is given here. So we can put this value of half life. So first is the half life is given here, that is 30 minutes. So we can use the K1 is equal to 0.693 and here is 30. So for K1 we got K1 for which temperature, 27 degrees centigrade. So here we will get value 2.31 into 10 to the power minus 2 per minute. Okay. Similarly for 47 degrees centigrade, so the second temperature, so here K2 will be how much, this is 0.693, and again for this temperature half life is this one. So here you will get 6.93 into 10 to the power minus 2 per minute. So we will get two half life K1 and K2. Now second question is energy of activation. So for energy of activation we can use this formula, 2.03 log of K2 divided by K1. So higher constant by lower constant, EA by it is your R, EA by R, and divided by 1 by lower temperature divided by 1 higher temperature. So putting all values, so if you put values 2.303 log of K2, you already know that it is 2.31 into 10 power minus 2 and divided by here this is given as 6.93. So again, so K2 is this is your higher temperature, 47 is lower temperature. So lower by higher we have to put here higher by lower. So this is higher temperature, so this is wrong. You put here 2.303 log of this is your K2 by K1. So K2 is this one. So here put here 6.93 into 10 power minus 2 divided by, keep this thing all in mind, this will be a 2.31 into 10 to the power minus 2. And again equal to KEA we need to find out, and R is given here 8.314, again lower temperature minus higher temperature. So this will be your 300 minus 320. So we need to find, so EA here it will be, so EA it will automatically come, that is 43850 joule per mole. Okay, or you can say 43.85 kilojoule per mole. Now third question is we have to find the energy of activation of the reaction, that is the delta H is equal to activation energy, that is the forward, minus activation energy of, that is backward. Okay, so we need to find the reverse reaction, that is the backward reaction. So again, so this is your given here. So again, energy is minus 50 kilojoules. Here it is given here minus 50 kilojoules. So EA is given 43. This is the forward reaction, 43.85 ms. We need to find out here activation energy for the backward reaction. So on solving, we will get here backward reaction will be how much. So this will be your, so minus, so come here 43.85 plus 50. So you will get answer 93.85 kilojoule per mole. So this is our answer. In the Arrhenius equation for the certain reaction, the values of A and EA are 4 into 10 power 13 per second, 98.6 kilojoule respectively. So if the reaction is of first order, at what temperature will the half-life period be? 10 minutes. So we have to find the temperature. So again we will use the same formula. So again, if you see the logarithm equations, Arrhenius equation, the Arrhenius equation is K into A to the power minus EA by RT. So convert it to logarithm form. So if you convert it to logarithm form, so you multiply by the log. So on multiplying log, you will get here log of, so here log of K, and this will be your log of A, and plus not plus, this will be your minus. So minus will be your again EA by 2.303 into R, and again temperature will be your T. So here we can write here this is T. So again we multiply by 1 by T. So this is there. So now we can put all values. So here K means again they have given your half-life is 10. So we can write here T half-life, and K is equal to 0.693 divided by, this is 10 minutes. 10 minutes means 10 into 60. So this is the K value. So we can put this value K over here. So K will be your 0.693 divided by 600. And this is equal to log of A. A is given here, that is 4 into 10 to the power 13 minus E. A is given here 98.6. Already you can see 98.6. So 98.6 and 2.303, and again multiplied by 8.314, and temperature is 1 by T. So on solving, you will get here temperature is 311.305 Kelvin. So this question is solved. So this is the mathematical base. You have to put the data and solve this equation, you will get answer. The time period for 10% completion of a first order reaction at 298 Kelvin is equal to that required for its 25% completion at 308 Kelvin. So if the pre-exponential factor for the reaction is 3.56 into 10 per 9 per second, calculate the rate constant at 318 Kelvin and also the energy of activation. So here we need to find the rate constant at 300 Kelvin. So for this and 18 Kelvin, so for this energy of activation for both the temperature will be same. So first we will find what is the energy of activation. So again you will use this formula of logarithm. First we will find this one, what is the time. So time, how much they are taking. Time period we don't know, only we know this one. Time period is they have given 10% of this thing. So we will use this first order reaction. So to find the time period, first we will use the first order reaction. So first order reaction is, we know very well, that is that is time is equal to 2.303 divided by rate constant log of A by A minus X. So again if we substitute all this value, so time will be is equal to 2.303 and log K is equal to 298. So for this temperature 25 centigrade, and log of this will be your 100 by 90. So this is one temperature, and the second is when it becomes 25 degrees centigrade. So again second will be your both have same temperature because they have given it is equal. So T of 298 is equal to T of, we can say, 308. So both are equal, so we can take it. So again this is equal to this one, so T 298 is equal, so again T for 308 is equal to 2.303 divided by K is equal to 308, and log of this will be your 100 by 75. So since, just cut it here, since we can say T of 298 is equal to T of 308, so what will happen, this will equal to 2.303 K of 298 is equal to log of 100 divided by 90 is equal to 2.303. Again, K of 308 is equal to log of 100 by 75. So on solving, we'll get here value of K 308 divided by K 298. So you will get this value 2.73. So this is nothing but the definition of temperature coefficient. Okay, now we'll use the Arrhenius equation. So again, you use the Arrhenius equation. So Arrhenius equation is nothing, so we know very well, that is the 2.303 log of, so here you put higher temperature, that is 308 divided by lower temperature, so that is 298. So again, this is equal to EA by R and divided by multiplied by 1 by lower temperature minus 1 by higher temperature. So just to substitute this value, on substituting value you will get here 2.303. so this will be a log this will be 2.73 we are taking from here this side. So put this value over here, and here you will get activation energy and divide by R is equal to 8.314. so and this is your temperature is 298 minus temperature is 308. so on solving you will get here EA is equal to, that is 18. This is, you will get in calorie, so 18.33 kilocalorie per mole. So this is our activation energy. Okay, so not here we have used 8.314. so actually you will get this is calorie after this one, actually you will get the value, this one 76.6227 kilojoule per mole. So you have to convert this into calorie form. Why we are converting? Because we will solve next problem. So again, after this one we have to reduce this one, we have to find the K 318. now we got the EA. So after EA, Arrhenius equation is, that is Arrhenius is how much given here, this is given at 3.56. so multiply 3.56 into 10 to the power, that is we know this value, K is equal to A e to the power EA by RT. so EA we know that, so EA is, that is 18.33. so we can write here not 18.33, right here this one 76.622, and again divided by temperature is RT is 8.318, and this divided by 318. so this is one value power over here, this is. Now so on solving, so here you will get, so just I am just pushing up 3.56 into 10 to the power 9, and if you solve it, so this will, you will get 2.59 into 10 to the power minus 13. so you will get answer 9.22 into 10 to the power minus 4 per second. so this is our second answer. The rate constant of a reaction is 1.5 into 10 power 7 per second at 50 degrees centigrade and 4.5 into 10 power 7 per second at 100 degrees centigrade. Evaluate the Arrhenius parameters A and EA. So again, this is easy, you can use this again same equation, 2.303 log of K2 by K1 is equal to EA by R, and this will be your lower temperature mass, again higher temperature. So just put this all data over here, so you will get here 2.303 log of this is the rate constant, higher rate constant, divided by 1.5 into 10 power 7. So the two rate constant is given here, just put this value. So again EA we need to find out 8.314, and temperature, two temperature is given here, that is one is 323 minus 1 is 373. So here if you solve it, here we will get value EA is equal to 2.2 into 10 to the power 4 joule per mole. So this is the first is the activation energy, and we need to find the pre-exponential factor, that is A. So rate constant we know that 4.5. so already if you take it, K is equal to E to the power, not A into E to the power divided by A by RT. So just we put this value, K is equal to 4.5 into 10 to the power 7, and A is already given here. So A value is how much? A we need to find out, and EA is 2.2 into 10 to the power 4, and again divide by here 8.314, and temperature is 373 Kelvin. So if you solve it, so here we will get value of A is 5.42 into 10 to the power 10. So this is our answer. This answer and this answer. There are two answers. So this is our answers. A first order reaction is converted to be, it requires activation energy of 70 kilojoule per mole, where 20% solution of A was kept at 25 degrees centigrade for 20 minutes. Then 25% decomposition take place. What will be the percent composition in the same rate in a 30% solutions maintained at 40 degrees centigrade? Assume that EA remains constant in this range of temperature. So this is the question given here. So A is converting to B. So for first we will find what is the rate constant at 25 degrees centigrade. So we will use the first order reaction. So for first order reaction, we know the formula, that is K is equal to 2.303 divided by T is equal to log of A minus A by A minus X. So just put this value. So K 25 is equal to, so here this will be your 2.303, and what is the time period? So time will be your given here 20 minutes, and log of, so A is given here. So what is A? So if you see, A is given here 20, and divide by this will be your 75% is decomposed, 25% equals, so 75% remain there. So we will take here that is 20 into 75%. So here on solving you will get answers, because this is the initial amount. So here you will get 2.303 divided by 20, and this is your log of 20 by 15. So on solving you will get here 0.0144 per minute. Okay, now we got this one K25, that is the rate constant at 25 degrees centigrade. So now with the help of that is Arrhenius logarithm equations, we will get the value of K, that is 40. So use this value logarithm, that is at 2.303 log of K 40 divided by K 25 is equal to EA by R, and this is your 1 by lower temperature by higher temperature. So we know this two temperature. So they have given two temperature, so that 25 and 40. So just put all this value 2.303 log of K 40 we don't know, K at 40 degrees we don't know, but 25 we know very well. 25 is 0. This is given here, so 0.144, and sorry, this is your 0.14, and EA is given here. So what is EA? That is a 70 into 10 to the power 3, and R is given here 8.314. So here temperature is 1 by 298 minus 1 by 313. So now we can calculate. So here if you calculate it, see, you will get the value of K40 is equal to 0.05575 per minute. Okay, now they are asking what is the percentage of decomposition at K40. So again we will use the rate constant value. Okay, so we can use this value. So just I am just keeping this one for convenience. So here K40 is equal to, we have the second equation, we have to find this one. K40 is equal to 2.303. so again T we require, and log of A divided by A minus X. So we can put this value because we need to find out this one, and because they are writing the same rate with 30% solutions. A, our initial solution is 30%. So we will write here K40, that is 0.005575 is equal to 2.303, and time is how much? That is 20 minutes, and log of 30 divided by, here it will be your 30 minus X. So what is X? So on solving you will get here, on solving 30 minus X is equal to 9.838. So this is our answer, 30 minus X. So again what will happen? So again we have to find the percentage of decomposition. So percentage of decomposition, we need to find out 30% solutions. So right here this 30% solutions will be how much? So right here it is this much, 9.8. This will be your, not this one, so this is there, so we have to write here whole, that is a minus x, that is divide by, here it will be your a into 100. So a we have taken already, that is 30 minus, this is given here, that is 30 minus a minus x, this is 30 minus, means we have to put this value 30 minus x divided by, here it will be 30 into 100. So on solving we will get here 30 minus 9.838 divided by 30 into 100, so you will get here 67.21%. So this is our answer.